Today, we'll learn a consistent method to differentiate logarithmic functions with any base value. The formula displayed on the screen is the formula we'll use today. When differentiating the log base a of box, the box moves to the denominator multiplied by the box prime in the numerator, which I always emphasize. However, there's one peculiar term multiplied in the denominator, which is a natural logarithm. To handle this, simply bring in the base value a from the left problem and make it ln a, then multiply it in the denominator. For those who have only seen the differentiation of natural logarithms, the term ln a may seem a bit unusual, causing this formula to appear slightly awkward. Why don't you try substituting a with e? Let's replace the a on the left and the a in the denominator with the natural constant e. Log with base e becomes a natural logarithm, and ln e equals 1. Therefore, the formula can be simplified like this. Similar to the differentiation of the exponential functions in the previous video, I have introduced the term ln a to demonstrate a consistent method of differentiating logarithmic functions with any base value. Let's explore this further through examples. The first problem is log base 3 of x squared minus x. To find dy over dx, let's use the formula shown in the top right corner. Since the base of the logarithm in the problem is 3, we'll substitute 3 for all the a values in the formula. Now, comparing the problem to the white box, you can easily see that x squared minus x should be placed in the box. We'll also put the same term in the box of the denominator on the right. For the green box prime, we need to differentiate the term in the denominator and place it there. The derivative of x squared minus x is 2x minus 1, which we'll put in the box prime. Rewriting the answer, we have 2x minus 1 over x squared minus x times ln 3. In the next example, we'll delve into natural logarithms. Let's differentiate y equals ln x to the power 4 plus x. Once again, we'll use the formula to find dy over dx. In this problem, the logarithm has a base of e, so we'll substitute e for all the a values in the formula on the right. Then we'll put x to the power 4 plus x in both the white box on the left and the box of the denominator on the right. Now, differentiating x to the power 4 plus x gives us 4x cubed plus 1, which we'll place in the green box prime. Since ln e equals 1, and the answer simplifies to 4x to the power 3 plus 1 over x to the power 4 plus x. We have just solved a problem involving the natural logarithm, and we can conclude that the derivative of ln box is box prime over box. Therefore, if we were to integrate box prime over box, it would naturally result in ln box plus c, where c is the constant of integration. This means that we can use a similar process in integration as we do in differentiation. In other words, integrating the result we obtained earlier, 4x to the power 3 plus 1 over x to the power 4 plus x, would yield ln box plus c with x to the power 4 plus x inside the box. We have now learned how to easily integrate fractions in the form of box prime over box. If you'd like to delve deeper into this topic, click on the link in the top right corner. In the next example, we'll explore a slightly different case of differentiating logarithmic functions. Let's differentiate y equals log base 2 of x to the power 4. Before directly differentiating, there's something we need to consider. This function has an exponent of 4, and before applying the derivative of the logarithmic function, we need to use the power rule to differentiate the outer exponent first. In a previous video, I explained a modified power rule that allows us to differentiate quickly without using the chain rule. The formula we used looks like this, and there's a link video in the top right corner for reference if you need it. The derivative of the box to the power of n is n times box to the power of n minus 1 times box prime. Looking at the problem, we can see that the box should contain log base 2 of x, and we'll change the exponent n to 4. Similarly, we'll change the n value in the formula on the right to 4, and we'll substitute 4 minus 1 for the exponent of the box, which becomes 3. We'll also put log base 2 of x in the box, just like on the left side. Finally, we'll place a differentiated term of this box directly into the adjacent green box prime. Let's bring back the formula we used for differentiating logarithmic functions. As you can see, the base value of the logarithm is 2, so we'll substitute 2 for the a values in the formula on the right. In the left box, we'll have x, and the box of the denominator on the right will also have x. and we'll place the derivative of x, which is 1, in the numerator's box prime. Simplifying this result, we get 1 over x times ln 2, and this value should be placed directly in the box prime on the upper line. Now, the final derivative of y is dy over dx equals 4 times log base 2 over x to the power of 3 times 1 over x times ln 2, or in fraction form, 4 times log base 2 of x to the power of 3 over x times ln 2. That's our answer. In the next example, we'll learn how to differentiate more complex logarithmic functions. Let's differentiate y equals log base 5, 1 over 2x minus 1 times x plus 2. However, if we directly differentiate this logarithmic function, we'll need to perform complex calculations to find the box prime. But if we utilize the properties of logarithmic functions, the problem can become much easier. Rewriting the fraction inside the logarithm as its reciprocal, we have log base 5 of 2x minus 1 times x plus 2 to the power of negative 1. And bringing the exponent negative 1 to the front, we get negative log base 5 of 2x minus 1 times x plus 2. Using the properties of logarithms again, we can separate the multiplication into addition. Negative log base 5 of 2x minus 1 plus log base 5 of x plus 2. Now, if we differentiate each logarithmic function separately, we can easily find the answer. To differentiate, let's use the formula in the top right corner and differentiate each logarithmic function one by one. For the first logarithm, with a base of 5, we substitute a with 5. Then we put 2x minus 1 in the box, and the derivative of the term 2x minus 1, which is 2, in the box prime of the denominator. Similarly, for the second logarithmic function, we substitute a with 5, put x plus 2 in the box, and the derivative of the term x plus 2, which is 1, in the numerator's box prime. Simplifying the expression for dy over dx, we have negative 2 over 2x minus 1 times ln 5 plus 1 over x plus 2 times ln 5, which is the desired answer. Remember, before differentiating logarithmic functions, simplifying the expression using the properties of logarithm can make the differentiation process much easier. In the last example, I will solve a more special problem. Let's differentiate y equals x to the power of x. Some students may attempt to differentiate it directly using the power rule, but since the exponent x is not a constant, we cannot differentiate it directly. What if we bring the exponent x down? Let's apply natural logarithm ln to both sides. The left side becomes ln y, and the right side becomes ln x to the power of x. By utilizing the properties of logarithmic functions, we can bring the exponent x down. Now let's differentiate both sides simultaneously. Although this part involves the implicit differentiation, we can solve it using the concepts we have learned so far. If you want to learn more about implicit differentiation, please click on the link in the top right corner. To differentiate the left side ln y, we'll use the differentiation formula for the logarithmic function. Since it is a natural logarithm, the base value is e, and we substitute e for a. Then the ln e on the right side simplifies to 1. In the left box, we put y, and the right denominator box, we also put y. Now, we need to put the derivative of the y in the box prime of the numerator, which is simply dy over dx, as you know. We have differentiated the left side of the equation, and the result is dy over dx over y. For the right side, x times ln x, since it is product of two terms, we'll use the product rule. It becomes x prime times ln x plus x times ln x prime, which simplifies to 1 times ln x plus x times 1 over x. Writing more simply, the expression becomes ln x plus 1. Now let's simplify dy over dx. If you multiply the denominator y on both sides, dy over dx becomes y times ln x plus 1. Substituting y with x to the power of x, the answer can be written as x to the power of x times ln x plus 1. How about that? When there is a variable as the exponent, we can differentiate by taking the natural logarithm on both sides. Remember the differentiation formula for the logarithmic functions we learned today, as it will be useful for integrating fractions later on. In the next session, let's study the differentiation of the inverse trigonometric functions. If this video has been helpful, please subscribe and like. Thanks for all for watching. This has been your Math Guardian, Alex.